unconstrained optimization problem. So the motivation for us to discuss the optimization technique because we want to develop some optimal paths. We want to develop some paths, for example, with minimum traveling time or minimum traveling distance. So we need to formulate a cost function or objective function. But typically, the cost function of our objective function are difficult to solve. So that's why we require the optimization technique. So for the optimization techniques, there are different set of techniques. So the first one, or the simplest category, is this unconstrained optimization problem. So the unconstrained optimization problem can be formulated like this. We try to minimize scalar called function. So a scalar called function of the u. So in this case, you should take care that this j is a scalar. And this u is a vector. So we generally define this u in a real n-dimensional space. So that means we define this u to be a column vector. Typically, we define this u to be the column vector from u1, u2 up to un. And all these components are real. That's why we define the meaning of this Rn. So it's an n-dimensional real space. N-dimensional real space. So this problem formulation is quite simple, right? So it does define a scalar function of multiple control input of u. So you can think about there, you can define multiple input to your vehicle. Eventually, for your vehicle to satisfy certain criteria. So now criteria is formulated by this scalar. By this scalar. So if you want to minimize the scalar so that the path can be optimized in terms of your criteria. So to solve this problem, so in generally this j is unknown. So we are not solving a particular function, but we want to find the general solution to this set of problems. So the general solution to this problem is to solve two conditions. So the solutions to this problem is to solve two conditions. So the first one is the necessary condition. So the necessary condition is to calculate this dj du and evaluate at this u equal to u star. And this equal to 0. So in this equation, I want to emphasize 2 points. So the first point is how to evaluate this dj du. So we know that j is a function of u1 up to un. And here is to evaluate the derivative of a scalar in terms of a vector. So based on the matrix calculus, this derivative can be defined. This derivative can be defined like this. Can be defined of is dj. This is a scalar in terms of u1, then dj in terms of u2, up to dj in terms of un. So from this we can construct column vector. So we know this column vector in the dimension of n by 1. So now because the dj is a scalar, the u1 is a scalar, so you know how to solve this, how to calculate this. It's just a general calculus equation. So you set this equal to 0. Set this equal to 0. So the solution, when you solve these n equations, so the solution to this one will be the u star. But in general case, this u star is not unique. So you may find multiple u star. So you know one u star means a point in the n-dimensional space. So from here you may solve, for example, you got a u1, u star 1, u star 2, something like this. So you may find, for example, m points, um star. So in the one-dimensional space, so just think about the one-dimensional space. So if, for example, you just got one scalar input, just a u1, and here you got a cost function, assume the cost function in this form. So by evaluating this equation, so in this one-dimensional form, you know you only got one equation. You only got dj du1 equal to 0 in this equation, because you don't have this u2 and un. It's just a one-dimensional space. So in this particular one-dimensional space, when you solve this dj du1 equal to 0, so the solution will be these points, these 4 points. So in this case, you will got this to be the u1 star, this to be u2 star, this one to be u3 star, this one to be u4 star. Right? So it's quite straightforward to understand. So the necessary condition will give you all the potential solutions. So now it's in the one-dimensional space. So this 1D space. So if you expand this problem to a 2D space, you may get, for example, 4 solutions. But each solution will contain 2 components. For x and y. Because for the 2D space, that will be a 2-dimensional space. So you got x and y for the control input. So you can also expand the problem to the n-dimensional space. So for the n-dimensional space, you may have m potential solutions. But each solution will contain n dimension. So this is the first set of equation. So the first set of equation is the necessary condition. So by solving this necessary condition, we will give you all the potential solutions. So the second condition is the sufficient condition. So the motivation for us to evaluate the sufficient condition is because from the first step, we can determine all these potential solutions. But some solutions are minimizing point, some are maximizing point. But we want to minimize the solution, so we want to distinguish the minimizing point from the maximizing point. So how to do that? That will be the sufficient condition. So in the sufficient condition is to evaluate the second derivative. So that will be the second derivative, dj square divided by du square. So evaluate at this particular point. So u equal to u star. So this needs to be greater than 0. Greater than 0 for minimizing points. So I also want to emphasize 2 points. So the first point is how to calculate this one. So you know, from here you know when you evaluate the derivative of a scalar in terms of vector, you got a vector. And when you do the second derivative, so actually you evaluate the derivative of a vector in terms of another vector. So in this case, you will got a matrix. So the general form for this matrix, so you can expect this matrix will be a n by n matrix because the u got n dimension. And the u got n dimension, and the second derivative got n dimension as well. So the matrix at here will be n by n matrix. So you can imagine that you will got an n by n matrix here. So the n determines how many components. So the n determined by how many control inputs you have. Here, because you got n control input, n by 1 scalar, n by 1 vector. So here you got an n by n matrix. So the general form will be something like this. So the dj du1 square, dj square du square. So this one is scalar. So the j is a scalar, u1 is a scalar. So you know how to evaluate this. So it's just a normal second derivative. So it's just a normal second derivative. And all the diagonal elements will be dj square du2 square for the diagonal elements. So this up to this dj square dun square. Then the first column will be defined like dj square du2 du1. So you may remember this order. So this order is determined by which derivative we calculate at first. So in this case, we evaluate dj in terms of du1 at first, and then we evaluate with du2. So this is the meaning for this one. So the second component in the first row will be very similar to this one. So it's a dj square, but with a different order. So it's a du1, du2, du1, du2. So here you can know the order of the derivative. But typically this component will be the same will be equal to this component. So typically, this will be equal. So your matrix is a symmetry matrix. But physically, you should know the order. You should know the order. So for all the elements in the first row, the last one will be dj square. So du1, dun. So in the first row, you evaluate the derivative in terms of u1, u2 up to un at first. After that, you evaluate in terms of u1. So the first column will be this one equal to dj square dun du1 so the first column will evaluate the derivative in terms of d1 at first, and after that you evaluate in terms of u1 to un. So from here, you know how to construct this matrix. So in a two-dimensional space, for x and y, you can imagine that your matrix will be 2 by 2. So for the three-dimensional space, this will be 3 by 3. So the first point is how to construct this matrix. So at here, you can imagine that all this matrix, all these components are the function. So not a particular value, but a function. So next is to evaluate the value of this matrix at these potential points. So we evaluate this u at the u star. So the u star is determined from here. So from the first step, you can evaluate the m points. So in this case, you put the m points into this matrix one by one, and this will give you a numerical matrix with numerical value. So this is the second point. So the first point, how to construct the matrix. The second point is to evaluate the matrix at this particular point. So the third point is more important, how to evaluate a matrix to be positive. So now the problem is how to evaluate a matrix to be positive or not. So for a matrix, so for example, we have a matrix of A, so this is an n by n matrix. So how to define this matrix to be greater than 0? How to define this matrix to be greater than 0? So the definition is defined in the linear algebra. I think maybe you still remember that. The definition is for any vector. So for any vector belong to Rn, so you know this vector is a n by 1 column vector. So for any vector, if this condition is satisfied, if this x transpose multiplied by A and multiplied by X, so we can check the dimension. So we know that if X is n by 1, then the X transpose will be 1 by n. So this 1 by n, this n by n, this x is n by 1. So eventually, this product will become a scalar. So it's a 1 by 1. So it's a scalar. So we know how to evaluate a scalar to be positive or not. So we already know how to do that. So the definition is if for any vector in the n-dimensional space, this condition is satisfied, then we say A is. So if we have this one, we can define this A is positive, is greater than 0. So this is the definition for positive definite. But definitely we cannot evaluate use this definition. We cannot check using this definition, because we cannot check for all the vectors in the n-dimensional space for this to be 0. So the more practical way is to evaluate the eigenvector. If for any eigenvector is greater than 0, eigenvalue, so we can check eigenvalues. So if for any eigenvalues is greater than 0, we can see this matrix is greater than 0. So this eigenvalue. Eigenvalues. Eigenvalues. So we know the eigenvalues for a matrix can be evaluated by this equation. So this lambda multiplied by identity matrix and minus this matrix, and we calculate the determinant. This is equal to 0. This is equal to 0. So this will give you lambda 1, lambda 2, up to lambda n. So in this case, so now we have this solution. So for any eigenvalues for lambda 1 up to lambda n, so if all the eigenvalues is greater than 0, then we say this matrix is positive. Yeah, you need to check all. You need to check all the eigenvalues. If any eigenvalue is smaller than 0, then you cannot say this matrix is greater than 0. So all the eigenvalues need to be positive in order for the matrix to be positive. So technically for the matrix, we don't say positive, but we say it's positive definite. But the meaning is to say the matrix is positive. So shortly I will use an example to show you how to solve the problem. So I think this knowledge is from your applicable mathematics. So if you already forgot it, I will suggest you to recap this knowledge. Recap the matrix theory, the linear algebra, how to define the eigenvectors, how to define the eigenvalues, and what the meaning of eigenvalues, eigenvectors. So the knowledge we require here is to evaluate whether a matrix is positive definite or not. So this will ask you to evaluate the eigenvalues. Okay, so these are the knowledge that we learned in the last week. So in this lecture, I will use an example. I will use a simple example to show you how to use this technique to minimize general function. So our problem will be defined as here. So we want to minimize scalar function of u. So in this case, u is two-dimensional. U is two-dimensional. So you can think about this to be x and y. So we want to minimize the function over a two-dimensional space. So you know, in a two-dimensional space, this cost function will span a surface. So we want to find the minimizing point in this surface over the space. So we will discuss an example. So our cost function is defined like this. So we have a 2u1 minus 1 square plus 3u2 minus 2 square. So in this case, we define this u to be u1 and u2. So before we solve the problem, so actually, because the function, this cost function is very special. So actually, you already know the solution. You already know the solution from your high school study. So we can intuitively inspect the function. So you know this cost function is a summation of two square components. So for this square components, for this quadrant components, you know for the real, all these values are real. So you know this u belongs to real, and only discuss the problem in the real space. So if the u are real, if the u are real numbers, so you know this one will be definitely greater or equal to 0. This one also greater or equal to 0. So the minimizing solution for this one is, so the minimizing point is achieved for this one equal to 0. So if this one equal to 0, you know this equal to 0. So also for this u2 equal to 0. So if we have this one equal to 0, this one equal to 0, so we know this will give us this j equal to 0. So actually this I put a star. So the minimizing point. So from here you can determine this u1 star equal to a half, and the u2 star equal to 2 divided by 3. So this u1 star, this u2 star, and this j star. So from here we just check, we just inspect the function by an intuitive method. So using the knowledge that you learned in the high school. But actually, we can solve this problem by the techniques that we just learned. So it's more general solution. So by using your knowledge from the high school, you know you can only solve this very special function. A special function, very special format. You can directly solve the problem. But our technique can solve any functions. So I will discuss two methods to solve this problem. So the the difference between these two methods are quite clear. So the first method is based on the scalar form. So the second method will be based on the vector form. So our technique is to evaluate the two sets of conditions. So the first set of condition is a necessary condition. So the necessary condition is to evaluate all the potential points, all the potential solutions. So this is evaluated by DJ du1. So we know this will be equal to 0. So evaluate the DJ du1. We check this equation. So this part is only in terms of u2. So this will become 0. Because we are evaluating the derivative in terms of u1. So this is a constant. So this is 0. And for this one will be equal to 2. So this 2 will move to the ground. So 2 multiplied by 2 u1 minus 1. So this will be equal to so 2 u1 minus 1, and remember you got another 2 at here. So you need to multiply by 2 to remember this, but it's no difference from the solution because it's equal to 0. So this equal to 0, this will give you, so this 2 u1 minus 1 equal to 0. So from here we can get u1 star equal to a half. So this is the first equation. The second equation is dj du2. So this is equal to 3u2 minus 2 multiplied by 3. So this is equal to 0. So this is equal to 0. We got 3u2 minus 2 equal to 0. So you got u2 star equal to 2 divided by 3. Right, so any questions at here? So by evaluating this necessary condition, we only got 1 point. So in the one-dimensional space, you can understand the problem like this. So for example, in a one-dimensional space, so our function is actually something like this. So you only got 1 point. You only got one potential point. So this one gives you u1 star. So we only got one extremo. But so far we don't know whether the extremo is minimizing our maximizing point. So to determine the point is minimizing, we only got one solution. But probably this one solution is a maximizing point. So the minimizing point is not existing. So to make sure that this point is a minimizing point, so you know from the necessary condition we got one extremo. So now the question is why is a minimizing solution. So you know the extremo could be a minimizing, could be a maximizing, could be a inflection point. So how to do this? This will be evaluated by the sufficient condition. So the sufficient condition, we know here we got U belong to R2, so it's a two-dimensional space. So from here, we know this equation will be a 2x2 matrix. So we know the sufficient condition is to evaluate this dj square du square. So in this case, we know we will got a matrix 2x2. We will got 2x2 matrix. So here are 4 components. We need to determine the 4 components one by one. So the first component is given by this dj square du1 square. So dj square du1 square. So this given by this du1. So this dj du1. So this given by so this du1. So this d for the equation for the dj du1. For the dj du1, we know this is given by this 4 multiplied by 2u1 minus 4. So this is actually given by 8u1 minus 4. It's given by this equation. So it's important that your first step is correct. So if you don't have 2, if you miss this 2, so eventually this will be wrong. So if you miss this 2, maybe in the first step the solution is correct, but in the second step it will be wrong. Because from here, I will show you, this will determine the eigenvalues. So by evaluating this one, so the 4 is a constant, so this will give you a 0. So this will be equal to, let's give just given by this 8. So this is equal to 8. So this is the first component. So you put the first component at here. So this is the first component. And here we are not evaluating this one at the u star, because this second derivative will become a constant. There is no u1 and u2 at here. But in the general case, this one will be a function, so it's not a constant. So if this one is a function, then you need to evaluate the value of this function at the extreme point. So here it seems that we are not using the extreme point, because this one already become a constant. So for the next component will be dj square du2 square. So this given by du2 for dj du2. So this du2 for the function, so for the du2, dj du2, that's given by this function. So in the 6 by 3 give you 18 u2 multiplied by 12. So if you evaluate this one, you know the 12 will be a constant, so it's a 0. So you got 18. You got 18 here. So the 18 will be So next component will be this DJ square du1 du2. So this will be du1 for DJ du2. So this equal to this du1, this DJ du2 given by 18 u2 minus 12. So this equal to so the 12 is a constant. So also the u2 is a constant because we are calculating in terms of u1. So this are constant. This are constant. So you got a 0. You got a 0. So similarly, we calculate this dj square du2 du1. So this equal to du2 is dj du1. So this du2. So dj du1 is given by 8 u1 minus 4. So we know all these are constant in terms of u2. So you got a 0. In terms of 0. So these two zeros will be at here. So now I just copy the solutions at here. So we have this dj du square equal to 8, 0, 0, 18. So we got a matrix. So this one is evaluated at u equal to u star. U star. We know the u star is actually given by half 2 divided by 3. So we actually evaluate this matrix at this particular point. But however, all these are constant in terms of independent to your point. So now the important step. We have not evaluated the sufficient condition. We just calculate the second derivative. Now to evaluate the sufficient condition is to check whether this matrix is greater than 0. So this is the question. So I put a question mark at here. We want to check whether this matrix is greater than 0. So to evaluate a matrix to be greater than 0 or not is to find the eigenvalues. So now we want to find the eigenvalues and to check whether they are positive. They are all positive. So this will be our task. So to find the eigenvalues, we evaluate the determinant. So it's lambda I minus this matrix is dj du square. Evaluate the determinant. So for this identity matrix, so we know the identity matrix is just easily defined like this. So it's 1, 1 is 0. So these are the identity matrix. So the identity matrix, the dimension is determined by a dimension of this matrix, because in this matrix we already got a 2 by 2. This matrix is 2 by 2, so we have this 2 by 2 matrix. So lambda multiplied by the density matrix equal to lambda multiplied by S1. So this equal to lambda 0, 0, lambda. Then a matrix of this matrix minus this matrix is just given by the subtraction element-wise subtraction. So it's lambda, the first element, lambda minus 8. So the second element is 0 minus 0, so it is 0. So the third element is a 0 minus 0, you have a 0. So the last one is a lambda minus 18, is lambda minus 18. So we got this matrix and we calculate the determinant. So the determinant is given by, so this lambda minus 8 multiplied by lambda minus 18, and minus is 0, 0 multiplied 0, minus 0. So this equal to 0. So from here, we know we got a equation lambda minus 8 multiplied by lambda minus 18 equal to 0. So to solve this equation, we know the first eigenvalue is given by the first component. So we have the first eigenvalue given by A. And we have the second eigenvalue given by the second part. So the second one given by 18. So here, because both eigenvalues, because lambda, so now we have lambda 1 and lambda 2. So lambda 1 and lambda 2, both greater than 0. Both greater than 0. So we can see this dj square, du square. So this matrix is greater than 0. So both eigenvalues are greater than 0. So we can see this second derivative of this Hessian matrix is greater than 0. So because this matrix, this Hessian matrix is greater than 0, we can see, because this one, so we can see the u star equal to a half 2 divided by 3. We can see this one is a minimizing point. Minimizing point. So these are our conclusion. So the necessary condition is to determine all the potential solutions. The sufficient condition is to determine whether the solution is a minimizing point or a maximizing point. So this is the first method. So before we discuss the second method, any questions? Do you have any questions about the solution to the problem? So the concept is quite clear. So the concept is firstly, you have this cost function. So from this cost function, you can check the input, how many input you have.
Maximizing and minimizing.
Because the number of inputs will determine the dimension of your problem.
No, you need
So here you got
yes, but this
two components, two-dimensional problem.
So are these two equal?
So by using the first answer
Then
equation, first answer equation, you will got a set of potential solutions. Set of potential solutions. Because here is a two-dimensional problem. So in each point, you will have two dimensions. So each point contains two components. So but you may have multiple solutions. If your function in this form, you got another point here, you will have two potential solutions. So the condition is to evaluate why these points are equal point. Because in the two-dimensional space, so you can expect that we will construct a 2x2 matrix. You can evaluate this one by one and construct this matrix. Then you determine the eigenvalues to check. So you remember that all the eigenvalues must be greater than 0. Even one eigenvalue is not greater than 0, then your matrix is not positive. So all the eigenvalues need to be greater than 0. So at here, the matrix is greater than 0, so we can see this one matrix. So if you have multiple potential solutions from here, then you need to evaluate this matrix one by one. So in this particular problem, we know this second derivative
Which makes sense.
is constant.
如果你这个是 0.5， 你这个是 0.666， 那你就懂了，就向上。
But however, in the general case, this function is not a constant. So you have to evaluate this matrix in terms of your potential points from here one by one. So for each point, you will got a matrix. So you need to evaluate whether it's possible or not. So for the next point, if you have multiple points at here, for the second point, you will evaluate this matrix again. So you will evaluate this matrix, the eigenvalues for multiple times, if you have multiple solutions from the first step, and your matrix is not constant. Okay, but all the procedures will be the same. So this is the first method. So the first method we deal with a very special form, only for the two-dimensional space. So imagine if you have three-dimensional or n-dimensional, then this will become very complicated, and cannot be evaluated with the computer. So the second format will be based on the vector definition. So the second method will be based on the vector format. So you may find this a little bit more complicated. So firstly, we want to use a vector format. Firstly, we need to develop the cost function properly into a vector form. So we have this J u equal to 2u1 minus 1 square plus 3u2 minus 2 square. And remember that we have this u equal to defined by u1, u2. So we can expand the equation. This becomes 4u1 square minus 4u1 plus 1. So this from first equation. From the second equation, this is 9u2 square minus 12u2 plus 4. So this equal to 4u1 square plus 9u2 square. So it's second order components, and plus minus 4u1 minus 12u2. So this is the first order components, and plus the constant, So for the second order components, so for the 4u1 square plus 9u2 square, this can be developed into a vector form like this. So the general vector form, so we define u as here. The general vector form is defined like this. So we have this u1, u2 multiplied by a matrix, and after that we have this u1, u2. So the motivation for us to do this is, so from here you know this one is a scalar. So this one you can see is a 1 by 1. It's a scalar. So for matrix eventually become 1 by 1. You know the outer dimension. Outer dimension in your matrix product need to be 1. So the first dimension for this one must be 1 multiplied by something. So the dimension for the last matrix need to be 1 for the outer dimension multiplied by something. So for the inner dimension, because here we just get two components, so that will be 1 by 2. So this one is the 2 by 1. So certainly we need to define this matrix to be 2 by 2, so that eventually the product will become a 1 by 1. And also, so because this is the first dimension, this is the first motivation to choose this format. So the second motivation to choose this format is we define this u equal to u1, u2, a column vector. So we know this one will be u transpose. So u transpose multiplied by matrix. So for example, I define this matrix to be F. So this u multiplied by F multiplied by u. So you can note, you may notice the dimension. So this u transpose the dimension of 1 by 2. This F is 2 by 2. This u is 2 by 1. This is the dimension. So now we already determined the format. We already determined the format So you know this format is quite similar to the one-dimensional problem. It's a one-dimensional problem. So for example, you only got U1, you know you got U1 transpose, this is equal to U1 multiplied by a constant F multiplied by U1. So think about the U1 is a scalar. So if you got this form, you know this equal to F U1 square. So we can see this one is a general format for this quadrature form. So it's just a general format. So it's just a general format for this quadrature format for vector input. So now we have determined the format. Then the next thing is to determine the components. So the components actually can be determined just by this 4, 9. So this 4 will be at here. So this one will be 0, this 0, this 9. So this 4 and the 9 will determine the parameters for U1 square and the U2 square. And these components will determine the component of the product of U1 and U2. So you can multiply this equation by yourself. You will find y of 4 and 9 at here. So this for the first part. For the second part, so this minus 4 U1 minus 12 U2. So for this one, we can define this to be something like this. So we know the dimension for this one is a 1 by 1. So for 1 by 1, we need a 1 by 2 multiplied by 2 by 1 to get a scalar. So it must be a format like this. So I define U1, U2 and here. Define U1, U2 and here. So we have this these two components. So it's 1 by 2. So this 2 by 1. Eventually you have a 1 by 1 matrix. So we define this to be another. So we define this. So from here you can see the first component will be minus 4. So the second component will be minus 12. So if you multiply this one, it will be minus 4 multiplied by U1 plus minus 12 multiplied by U2. You have this one. So I just because we typically use column vectors, so I just define this J to be minus 4 minus 12. So I just define a new vector in this format. So if I define a matrix, I define a vector in this format. We know here we got a J transpose multiplied by U multiplied by U. So now the cost function can be formulated in a vector form. So we have this J U equal to, so the first part is the U transpose F U plus J transpose U plus H. And all the matrix vectors can be already defined. So the F is a 2 by 2 matrix. So it's the 4009. So the G is equal to -4, -12. And we have this H equal to 5. Okay, so now we have already formulated the problem in a vector format. So in the next lecture, I will show you how to solve the problem by using the vector format.
大的，我也想。6楼，不去，全部在6楼，因为6楼18楼，18楼是不是？然后那个男厕所最主要的，然后不能男厕所。然后我上日语那个日语老师说的日本嘛，如果说这女的排队排太长了，不用排队啊，是的，然后有一个女的在外面。啊，可是如果里面有人。